Okay.
Just wait for the record button.
So everyone can see the slide, right?
Yeah.
So I'm going to talk about applications of Young diagrams, mostly on SN and SUN. So in class, we have studied a bit on the correspondence between irreps of SN and Young diagrams, but we haven't established that completely. So I'm going to do that first, and then I'll talk about induced and restricted representation of SN, as in if Sn is given, if an irrep of Sn is given, then uh, uh, I mean, how it is a direct, like, how do I get Sn plus 1 irreps from irreps of Sn? And again, restricted is how I get irreps of Sn minus 1 when irreps of Sn are given. And then I will talk about direct product of irreps of Sn. And then I'll move to SUN. First, how to write irreps in form of Young diagram, SUNs, irreps in form of Young diagrams. Then its dimension and how SUN and SN are related while I use direct product of irreps of SUN. So let's start with the from where we left off in class, that we took a subgroup of Sn, which is S lambda 1, S lambda 2, a direct product till S lambda n, where lambda is a partition of n. And uh, so the compound character was given by this factor, where alpha, beta, and gamma basically define a class in Sn, and this basically is a coefficient of x1 to the power lambda 1, x2 to the power lambda 1, lambda 2 in a multinomial which looks like this. This is the and here is general definition for multinomial expansion, and why I'll get uh, the coefficients as these numbers. So we like you guys got it right. Can I move on to the next slide? Um,
Are there any questions about this particular multinomial, for example? I think it's okay.
yeah. Okay.
Everybody.
So now I can rewrite this multinomial when I rewrite the cycle structure alpha, beta, gamma as a partition. So uh, so that multinomial essentially becomes this multinomial. And also we notice that for this compound character is for a particular partition of lambda. So we can roughly say that this partition lambda corresponds to a particular irrep, and the so this character is the character of the class C with alpha, beta, gamma cycle structure of the lambda irrep. So using that, we using this multinomial, the coefficients of this multinomial, we can get the dimension uh, of the representation when we take the character of the identity element. So my mu, which is identity, is one like n one cycles, and the coefficient. Uh, so we need the coefficient of uh, this for any rep lambda in this multinomial. So that by just using this formula we will get the coefficient as this, and also by just looking at I mean that also gives the motivation why we took this as the subgroup, like how why we started with s lambda 1 uh, cross product s lambda 2 and so on. And we will call this space where all my ereps corresponding to some lambda, like for a lambda we call uh, this space as the permutation module. uh, it's basically a vector space, and it has basis, and also we will look for the basis of this permutation module. And here's an example for S4 using uh, uh, the the coefficients. I mean, we used the formula and we found out the coefficient. We can see that these are all compound characters and not simple characters. And by I mean, so we need to get simple characters. So by just choosing some part of m lambda, we can achieve that. That will come after I discuss the basis for m lambda. So so uh, I define a tabloid as uh, okay, so if I take two lambda tableaux, T1 and T2, they are uh, row equivalent if their each of their row contains the same elements, and they all form a class, and a tabloid represents one such class. So for a given lambda, I'll have uh, a set of tabloids. So here is a example for this T, which is 1, 2, 3. This is one T which belongs to this tabloid. And when you're writing tabloids, you do not put those lines between numbers in the rows, because that's how you denote a tabloid. And uh, we also uh, define the action of Sn on these tabloids, so that basically what we will do is say that some form of these tabloids are form the basis for m lambda. So we need to uh, define the action of elements of Sn on the tabloid. So uh, I've acted the permutation 1, 2, 3 on this tabloid, which basically replaces uh, the entry with so if this is pi, then this entry is basically pi 1, and this is pi 2, and so on. And this action is well defined because uh, it it it's conserved under like it when you act the permutation on it, it moves to the same class, basically defined by this uh, condition. Like if T1 and T2 belong to the I mean is the same tabloid, then if I act pi on them, they become the same tabloid. So basically, the basis for m lambda is the set of all lambda tabloids. Like for a given lambda, how many ever tabloids I can get, that's the basis for m lambda. So here are some examples when my lambda is a n cycle. Whatever element of Sn I act on this, I will get the same tabloid. So this is a one-dimensional space. So this is the trivial representation, and uh, again we'll look at this example where lambda is n minus 1 comma 1, and we'll get four tabloids here, and we see that for for S4 for S4 this is a 3 1. So in the character table for M31 we have a four-dimensional representation. So 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 we have four basis vectors of it over here, and I know we have calculated the dimension of m lambda before using the multinomial, but even combinatorically we can count the number of tabloids we can get for a given lambda, and it turns out to be the same. And here I've written lambda L because I'll take only the non-zero lambda with same lambda 1 greater than equal to lambda 2 and so on. I just won't take the zero element. And that's how we will use for the rest of the uh, presentation as well. So since we want a part of this m lambda, so that we'll get simple characters. We define
So
s
just to
lambda,
clarify it, you
which is a
these
sub.
representations that you're talking about, the tableaus do provide representations, but these are reducible representations in general, right? So then you'll have to try to
Yes,
look at
yes,
invariant
yes, sir.
subspaces, whichever way. Okay.
Yes, sir.
Okay, go
Yeah,
ahead.
that's what I meant. Yeah. So we will define this space S lambda using some other basis vector and see how that will give us simple characters. So basically, irreps is what I mean. So to define the basis, we will need something called uh, polytabloid. So for that, I am defining something called a row group and column group, which is basically a subgroup of Sn, which fix for a row group uh, uh, it fixes the rows of the young tableau, and for column group it fixes the column. So a polytabloid is given by this equation where pi belongs to the pi permutation belongs to the column group, and this is the sign of permutation pi, and which acts on a particular uh, uh, tableau T. And so if I take this same T, this is 4, 1, 2, 3, 5, whatever, and uh, I find the polytabloid, which gives me this. So basically, it's, uh, I mean, you can see it's 4. I've shifted 3 and 4 here, and that's a odd permutation. And here 1 and 5, so that's an odd permutation. Here I've 3, 4, and 1, 5 are shifted, so that's even permutation. And uh, for S lambda, uh, the basis is given. The basis is given by all the polytabloids ET, where T is a standard lambda tableau. So how many ever standard tableaus I get for a given lambda, that is the dimension of uh, S lambda, uh, and E of T gives me the basis of that. So here is an example when my T is a n cycle, and all the uh, permutations that fix the column. So basically, this tablet is fixed by entire of Sn. So This is again the trivial representation, and here for lambda is n one cycles. Uh, if I take another t and I find e of t, so basically if I act some permutation which belongs to the column group, either I will get uh, the same polytabloid. I'll get the polytabloid with a minus sign. So it's basically one basis vector. So again, this is uh, one dimensional. So this is a from here we'll move to the theorem which states that uh, for every partition lambda of n, all the s lambdas gives us the complete list of irreducible representations for Sn. Uh, so this theorem also kind of shows that there's a bijection between number of irreps and young tableaux with n boxes. This is young tableaux with n boxes. Uh, Here the dimension is the basically the number of standard young tableaux is given by n factorial by product of hook length. This we had done in class as well. So here's a example. I mean, this is how hook length is defined, and now we use the uh, Frobenius formula for finding the simple characters. So similar to what we had done for m lambda, we find coefficients of x1 to the power lambda 1 plus l minus 1, and so on in this polynomial. So where lambda is the like lambda represents the erupt and mu is the class at which we want to find uh, the character. So there's another way to get dimension. This is not exactly. I mean, I haven't calculated the identity for a given lambda. I mean, that does give the dimension, but the formula I've used here is from a book where they find determinant and stuff like that, which basically again gives n factorial by hook length.
Yeah, but which book is that? Just for
Ah, I,
you have a
I,
reference list. You should have a reference list at the end.
yeah, can I add it in the end because I've
Okay,
read
okay, that's
some,
fine.
yeah.
That's fine.
Oh shit. Yeah. Yeah, now we move to induced and restricted representations of Sn. So if I have a erep in say S5 and I want to see, I mean, what happens to that erupt when we go to S4 is basically that does not stay an erupt, and it becomes a reducible representation. So in S4, that same erupt that was in S5 is will become a direct sum of erupts in S4. So so here, using young tableaux, I haven't drawn the young tableaux, but given lambda, I can draw young tableau. So for S15 for some irrep given by 5442 is the number of ways I can remove one box from this lambda tableau such that it still is a young tableau. So So I can remove one from the first row. It's still a young tableau. I can remove one from the. I can't remove one from the second row because then it's not valid. And so on. I can. So it's the direct sum of these S14 irreps. And induced representation, similarly, if I have uh, S15, then add one box to this lambda tableau, I will get uh, uh, that S15 is a like that irrep in S15 is direct sum of the irreps in S16. So uh, recursively, I will define a particular irrep in I I can define it recursively as like all the mules okay, I didn't actually
Sorry, are you saying something? Because can't hear you. Can others hear her? Or have I
notation
lost
sir.
contact?
No, sir, I can't hear as well. Yeah.
So hello.
Okay, she's saying something, but okay, could you just slow down a bit? Maybe your connection is a bit too bad right now.
Hello.
Hello? Are you
Hello.
yeah, you're here. Right.
Yeah.
Go ahead. We couldn't hear whatever you said a while ago. So,
So I can define this same thing recursively, as in starting from uh, like a null representation. I don't know what that null representation means. Like I add one box, then to one box, how many ways I can add another box, and so on. And I can there's something called a young lattice which represents uh, this this recursive thing. This is the young lattice which I was talking about. Uh, so this is the S1 irrep, and these two are S2 irreps, and these are S3 irreps, and so on. And one uh, one interesting thing about
sorry, I think we lost contact again, or at least sound. Could you try exiting and coming back again? Although there's no reason why that should work. Can one of you call her up and tell her that we can't hear? Or am I the only one who can't hear her?
No, sir. I can't hear her either.
So if somebody has a number, yeah, she has left now. If she joins again, it should be better sometimes.
She just messaged that she lost power,
Okay, okay, okay.
no Wi-Fi connection.
Oh, that is that's the reason. So we just had a zombie screen for a while. That happens. Is it possible for her to come back today? If she lost power, then we never know for how long.
Let me ask her if
Could you ask her whether she thinks it's possible to come back or whether we can reschedule this? Because we have to reschedule this for Sagar anyway, one of these days, next week. So,
yeah, we are asking, or just ask.
She said she'll be able to come back.
okay.
She's trying.
Okay, that's fine. We'll wait. Yeah. So you're back. Right.
Yeah, I had lost power, so
Yeah, yeah.
I
We realized that a while later when we saw nothing, everything frozen. Doesn't matter. Just try to get back where you were. You were talking about the young lattice.
yes, sir. Yeah. So one interesting thing about this is, without even writing out all the standard young tableaus to get the basis, we can just count the number of paths to that particular young diagram. So, for example, if I take this young diagram, there are three ways I can go to this young diagram. So, one way is like this. There's one way like this, and there's another way like this. So I've written those three parts, and those give me all the standard young tableau. And we we, we see that I mean, since we say this is the basis, the dimension of this irrep should be 3, and we get 3 paths. So we can use young lattice to find out the dimension as well. And, and we can also get the standard young tableau by writing like so. We added this box first, so we write 1, and we added a box next to it, so that box becomes 2. And then we next to 2 we added the third box, so that's 3, and the last is 4. And similarly for the other 2 parts as well.
So basically, you're adding one box at a time and keeping in mind that the thing has to stay in young tableau. That is, the number of rows, etc., have to strictly, number of elements in a row or number of boxes in a row have to strictly, well, not strictly, but strictly
Which
non-decrease,
decrease.
rather. So that's the way
Uh,
in which you build up the lattice.
no, sir. If you see the last thing, the numbers need not
No, no, I'm not talking
decrease.
about that. I'm saying when you go up the lattice, you started with one box,
Yes,
then you added one box to it that can either go to the left or below. That, of course, is
yes,
rather obvious.
yes,
Then when you add a next box, you start with this, whatever you had. You keep on adding one box in such a way. Say, this will not be apparent at this stage, but for example, if you look at the middle top one,
this,
now, yeah, when you add a box to this, you can add a box to the top right,
yeah,
but you
or
cannot add that or to the
yeah,
bottom,
yeah,
bottom corner, but you cannot add, say, to the second row, because that would
yes,
violate the basic structure of a young tableau.
yeah. When we're adding, we need to make sure that it's still a young diagram.
Yeah, keeping that in mind is how many ways you can fill this up, and then it's just the order in which you fill this up that gives you those numbers,
Yes,
the
sir.
1, 3, 4, 2, and so on.
Yes, sir.
So the last line will be 1 first, then below that will go 2, then to the left of 1 there will go 3,
Right.
and finally to
Yeah,
the left of that will go 4.
yeah,
Okay,
yeah.
thanks.
Okay. So now we see direct product of irreps of Sn. So we'll start with an irrep in Sn and an irrep in Sp. Uh, this N and P need not be equal. We can take the direct product, and we will get a irrep in for we'll get an irrep for Sn plus p, and these C, gamma, alpha, beta are the multiplicities of each of the irrep, and we will use Young tableaux to find out the RHS. So the motivation here is basically for since this belongs to Sn and this belongs to Sp, we will create two subgroups of Sn plus P, which is H1 and H2, such that uh, H1 permutes only n indices from 1 to n plus p. Like if you take I1 to In, which are n indices of from any n indices from 1 to n plus p, uh, H1 permutes those indices, and H2 permutes the other uh, n, like the other p indices. So there are n plus p c n times n possibilities of selecting these n indices and hence these indices as well. And we see that these subgroups H1 and H2 are isomorphic to Sn and Sp, and this is where the product of any element, like one element from H1 and one element from H2, gives S and P, but their direct product is not S and P. And also, uh, when we're relating it to the theorem we did in the first class, here also H1 intersection H2 is identity, but they're not normal subgroups of Sn plus P, uh, and their direct product also does not give Sn plus P. So we will see how this all connects when we like by the end of this discussion. So we take one irrep in, this is S4, and the direct product. So we label one of them, uh, like the first rows with A's, second row with B, and if there are third rows, then C's and D's and so on. And one by one, first we take the A's and then put it on uh, this irrep, such that uh, it's still a Young tableau. Also, we cannot have two A's or two B's in the same column. So these are the two rules for putting the A's. So we'll after putting both of the A's, we'll have these 5 diagrams. Uh, so is everyone clear till here? Hello.
Yeah, so if
Yeah.
somebody has a doubt, please ask.
Okay. Uh, so, uh, but there is one more rule when we are putting in B's and C's and so on. So, when you're counting the number of these ABCs starting from the right, and then we move to the second, then the third, then like as we move, we're counting the number of A's and B's. At any position in the box, the number of B's should not exceed the number of A's, and number of C's should not exceed the number of uh, B's, and so on. So here for this diagram, if we take at the very first box itself, the number of B is 1 and number of A is 0. So this diagram is not valid. But this diagram, on the other hand, is valid because there's one A till now and there's one B. They can be equal, but the number of B should not exceed A. And here number of B is 1, A is 1, and here number of A's is 2, and number of B is 1. So this is valid. So next we put this B in these diagrams following all these three rules. This 1, 2, and 3 rules. So uh, we get the set of these diagrams, and we there's 1, 2, 3, 4, 5, 6, 7, 8 diagrams, and two of them are same. Uh, we These two diagrams are the same. So uh,
Sorry, which two are the same? I lost your audio for a while. Or if you're still speaking, then we can't hear you.
uh,
Yeah, I can hear you now. So you said two diagrams are the same, but I couldn't hear or I couldn't see where you were pointing at that time because the audio got lost for me. Which two are the same? Hello? Okay, so there are two of those cell conjugates. Yeah.
the dimension of this entire representation is will be dimension of this. I mean, basically adding the dimension of each of these irreps. So that when when the multiplicity is 2, then you count it twice. So we get the dimension of this irrep as 210. Uh, but on the RHS, this irrep is three-dimensional, and this is two-dimensional. Yeah, no, this yeah, this is two-dimensional. Like we'll use the n factorial by product of hook length, and we find the dimensions, and that we multiplied by this 7C3, because that's how like we can permute, like so this S3 over here forms that group H2 which I talked about over here, which first selects some three elements of S and P and permutes that, and there are 7C3 ways of selecting those three. So the dimension on the RHS will also be 210, and 7C3 is equal to 7C4. That's and that'll be true for any dimension of the initial irreps we take. And the direct product of these Young diagrams are also commutative. So this ends the discussion for Sn, and we'll move to Sun. Uh, so for Sun, first we need to know how we can write the irreps as Young diagrams. Uh, we'll notice that there are n square minus 1 generators for SUN, out of which n minus 1 of them form the uh, Carta subalgebra, and the rank of SUN is n minus 1. So uh, I'm I haven't read a lot about the erepts of SUN, but it's it's given that an erupt of SUN can be defined by n minus 1 numbers, where one of them uh, uh, is the highest weight vector. Like an erupt can be described by the highest weight vector. For example, uh, uh, J. Like when we take J, I mean, all the values run from minus J to plus J and so on. And uh, so uh, the erupt has a dimension D, and this d-dimensional vector space is spanned by uh, a basis which is again represented by these n minus 1 numbers. So what I'm trying to say is, for every erupt, these n minus 1 integers will define it. So a fun and these are called Dinkin integers. In some in some text, I will provide the references. Uh, and so the fundamental representation is given by so if for SUN this is a this its length is n minus 1, so the fundamental representation is given by 1 and the others are 0, and that is represented by just one box. And this is a example here. Uh, for SU3, the length is 2. Basically, what these numbers say about uh, these the Young diagrams is that uh, if I have M1, M2, M3, and so on, uh, Mi is the number of columns with length I. So uh, if I have 0 to 0 0, so I need to have, so since m2 is 2, I need to have two columns which have the length as 2. So I'll have this, and
Sorry, we may have lost you again. At least the audio.
we have
Still lost.
hello,
Yeah,
hello.
I can hear you, but we just from 0 to 00 we heard nothing else. And still, okay, apart from the hello, I heard nothing else. It's from 0 to 00. You showed us the two boxes with two columns each, and then you were mentioning
From
1100.
where
I think
could
we
it
got that. Is that the same for everybody? Because I'm not sure whether everybody else heard the same thing. Were you describing the SU3 triplets? Hello? Were you describing the SU3
oh
multiplets?
no sir, I haven't started.
You haven't come to that yet.
Hello, no, I
Okay.
haven't. No, sir, I haven't started. No.
But again, can't hear you. No, can anybody else tell me whether it's my problem or whether everybody else has the same issue?
No, sir, it's the same problem.
Okay, that means there's something wrong at your end, at least some connection issue. Okay, so SU3? Yes. Everybody's video and audio are switched off, right? Apart from us and mine, of
Ye-
course. Right now, the audio is on.
can every
Are you back yet? Because your screen is still showing you lost your network connection.
I can hear you, sir.
Okay, so what you want to try start presenting again? Maybe stop the presentation, start again. So what we can see is your screen. Your screen
Yeah.
apparently is showing you lost your network connection, or else it's frozen from last time.
No, I have lost my connection. I think the power came
Okay,
back.
that's a possibility.
Yeah. Okay. So uh, for SU3, these are, I mean, this is just example for how to write the Young diagrams. We will, this is the trivial representation, the 0, 0 part. And when we'll see further that any column with length n, we will ignore that. Uh, so the maximum length of the column will be n minus 1. I mean, we uh, because even we have only n minus 1 integers, and uh, each integer says how many number of columns of that length. So the maximum is n minus 1, which says how many n minus 1 length columns we can have. So this corresponds, this singlet is basically, I mean, we will ignore it when it comes in bigger representations. Uh, so these are the other irreps for given this tuple. Hmm. We can also get, so once we have uh, 1 comma 0, the conjugate of it we can also get by replacing all the columns with length k. We replace it with length n minus k. So if we take the fundamental representation for SU4 and we take conjugate of it, we'll get uh, 0 comma 0 comma 3. So this is that representation, and similarly we'll get for other representations of SU4 as well.
Now, I
Uh,
think 0 comma 0 comma 3 would really have meant what? Three
uh,
columns, right? Of
oh
three,
no, yeah.
three.
So
It's
0
actually
comma
not 0
0
comma 0
comma
comma
1.
3. It's 0 comma 0 comma 1.
1. Yes, sir. Sorry for.
And
Yeah.
that's what you're saying is since you're one column here, one element in the column in the box here, that would have been 4 minus 1. So
Yes.
that's the n minus k.
Yes. Yes. And if we take this irrep of SU3 and take conjugate of it, uh, I'll I'll get these two boxes, which for SU3, I mean, I'm taking conjugate and then conjugate again. I'll get conjugate of the fundamental representation. So this also shows why we can ignore the column of length n, capital N. And there's one more uh, fact about the Young diagrams for SUN is that the rows uh, are like they give symmetrization of the irrep, and the column gives anti-symmetrization. I did not get a insight to that. I just written it down because it's used later. And so once we have the like now we've defined Young diagrams for irreps of SUN, and to get the dimension from the Young diagram, it's slightly different from what we did for the permutation group. First, we for a given n, we write down for the Young diagram n plus 1, like we increase it along the rows and decrease it along the column, and we take product of all of those numbers, and then we have hook lengths as usual. We take product of all of those hook lengths, and the dimension is given by this quantity divided by the product of hook lengths. So if we take for SU3, uh, we will have since n is 3, we have 3, n plus 1 4, n minus 1 is 2, and here it's the hook length, and we multiply and then divide by this, will get 8. So this basically represents a octet, and similarly we can get these dimensions uh, from the Young diagram. Like we'll get for example, if we take this decuplet, so it's 3 into 4 into 5 divided by 3 factorial. So that's basically 10. So we'll, given a Young diagram, we'll get the dimension of the erect. And now we'll move on to direct product of irreps of SUN. So each irrep basically acts on a, a vector space, and we will start with a fundamental representation which is n dimensional, and let that irrep act on uh, n-dimensional vector space V, which has basis defined by E subscript A. And we start with the fundamental representation because we can get other irreps using direct product of the fundamental representation. So first we'll take V direct product V when uh, we'll just start with one direct product. So the basis of that vector space will be given by EA cross EB uh, for these A and B's from like any A and B from 1 to n. Each of the basis vectors can be decomposed like this. So this is the symmetric decomposition. This is the anti-symmetric decomposition, and this also we can get by acting the s the irrep of S2 on the indices A and B. So we take the trivial irrep and act on AB, we'll get AB and plus BA, and we take the sine irrep, which has which will give me the anti-symmetric part. So uh, we have to see that we'll need n into n, so n square basis vectors. So we'll get n square basis vector because we do this decomposition for all indices a and b, so like for each of this vector. So uh, and this basically decomposes into invariant spaces. So this is one invariant space, and this is another invariant space. And for L, for okay, so I haven't said what L is. So we take direct product of VL times, and for L is equal to 2 we saw this case, and for L much greater than 2 we won't just get the symmetric and anti-symmetric parts, we will also get uh, the decomposition such that they're not symmetric or anti-symmetric. So to find invariant subspaces of L copies of V, uh, we use the SL group. So we use all the irreps of SL to get all the different permutations of the indices, like how we acted S2 on AB. So if we have uh, uh, direct product of VL times, we'll have A, B, C, D till L, and for uh, each of those A to L's, we'll get a particular decomposition. So, for example, we'll take L is equal to 3, and we'll take the first irrep of S3, which is the identity irrep, and the basis here will be given by uh, so we act S3 on so it's all the identity irrep. So we do all the group elements on the A, B, C, and we get this basis vector. And since we here also uh, we will, since we started with the fundamental representation of
Lost again, it seems.
will
Oh, yeah,
hello.
go ahead. Hello?
And again we'll get a basis.
Yeah,
Hello,
we can hear your hello, but after that,
slideshow is gone.
no slideshow we can see. We couldn't hear you.
It's better now, sir.
Yeah, it's better, definitely better.
Yeah.
Okay, how many more slides do you have? Because, okay,
Uh,
despite the
it's
fact that you did have some interruptions, it's already more than nearing an hour now.
yeah, it's almost over. Five
Okay, but you
five
can
minutes.
summarize the rules also at the end. That will be useful. Because even if people don't take away the actual definitions, which or work or or the derivations, at least the rules that you have to use, they are pretty
Okay.
useful. Okay, anyway, go ahead. Go
Okay.
ahead.
Uh,
No, I can't hear anything.
ABC into one again.
Sorry, we can't hear anything again, I guess.
Uh, Hello, hello.
Yeah, we can hear you in the bits and starts, but not continuously, seems.
నెట్ బాగానే లేదు. పర్వాలే. హలో. Oh my god.
Yes, I think we
No,
can
we
hear.
can hear the oh my god and the other conversation. But yeah,
Sorry. Okay, can I carry on? Can you see my slide?
Yes.
Okay. Okay. So the number of direct reps of the number of stamp. So we have taken Barian uh, is also the same column will give me 0. And the reason why we have this
sorry, it's actually breaking.
low
You're breaking up.
uh,
So could you just go slowly?
uh, is and we need to okay so we such that order and we make sure that in in one
Excuse me, I cannot see the slides on my screen.
No, that might be because you may have pinned something else. Can you check?
No, sir. It
pinned.
says Shaharika is presenting, but it's
So
showing
you
up
may have
black.
pinned her. You can see two different Shaharikas. One is Shaharika, the other is Shaharika
two
presentation.
flavors come. So now we'll
Okay.
see
If you
that
unpin
U
that,
U U D
automatically the presentation should
D
Yes,
come.
sir, sir.
Otherwise, you
It
can
came.
pin the
It
presentation.
came back on.
D
Yeah, but anyway, your audio is still not audible. I guess what we can do today. Can you hear me? I'm not very sure whether you can hear me either.
all these
Uh, no, sorry, we couldn't hear whatever you are saying. So maybe what we will do is we will postpone this part. This is a small part, right? 10 minutes at most? Or how long? Can you hear us?
Could she just message in the chat box? Then we might be able to see what she's saying.
But then typing the whole thing out in the chat box is not really very convenient, right?
yes sir, it's almost over sir, just
And since she is presenting, she wouldn't be able to read the chat box.
one more slide left.
Okay, one more slide. Okay, one thing we could do is since we couldn't hear the last slide.
I have just one more slide.
Okay, go ahead.
Hello.
Go ahead. Yeah, this is the one which we are most interested in, I guess. Most
Yes
people
sir.
would be.
Is have few there of mixed symmetry. So this is a singlet because three, and we'll have 3 into 4 into no these are not I'm just writing a combination inside S3's irreps and these UUD, UDD, and the other 4 uh, combination where I have 2 of the same quarks and the other is different. Hello. Yeah. Uh, this is a singlet and this gives me a doublet, and so those give me a singlet and a doublet. So and UDS gives me one symmetric singlet, 2 doublets, and 1 anti-symmetric singlet. So counting all of that, I'll have total 10 singlets coming, 3 from here, 2 from here, and 5 from these. And I have 8 doublets, 2 from here, 2 from here, and 4 from here. And then I have one anti-symmetric singlet. Uh, so the multiplicity of these basically gives me the dimension of the SU3 irrep. So I will have 10 symmetric singlets. I mean, I've counted that, but I can find out the dimension as well using the formula that I have given before. And this is this irrep is given by 3 comma 0, and this is the octet, and this is the singlet. And uh, so these are other examples. So if I have if I have a the fundamental representation of SU3 and its conjugate, I'll use the same rules I have used for Sn to get the direct product for Ereps in SU n as well, but the dimension that we calculate will be different. So the Young diagrams will be the same. The dimension is different. So this and now we have three quarks. The direct product of those three quarks will give me. Uh, I mean, we have calculated this before over here, here, and calculating the dimension for each of this, I will get uh, uh, 10, 8, 8, and 1. And there's another example where I can get the adjoint representation uh, of the which is of SUN, which has dimension n square minus 1. I will take the fundamental representation and take direct product with its conjugate. I will get a direct sum of the adjoint representation plus a singlet, and and that ends my presentation.
Yeah, so are there any questions? Because anyway, we should clap first. But this was the audio was interrupted, but you did very bravely and ended up properly. So that's great. However, questions? I would urge you to ask if you have confusions, especially about the final rules, because you should realize that those rules are things you will use, especially in particle physics, for example. You would use them a lot. The last slide that she showed essentially was quarks and antiquarks making mesons, or three quarks making baryons. The standard 10 plus 8 plus 8 plus a decuplet, two baryon octets, and a singlet. The entire particle structure that you have in the quark model. Of course, if you want to do, say, other symmetries like SU4 or SU5, higher flavor symmetries and so on, you would have to know how to handle the rest as well, the general case as well. Any questions, or everything is clear? And you said you would give us some references. Right? We need a few references as well. Which book, when you mention it's in a book, which book? For example.
I had some stuff opened in different tabs. I didn't take note, but it's there in the history. I will put it in the PPT and I'll mail it to you.
Yeah, and everybody, by the way, please mail your presentation to me. Because that's part of the records anyway. I also have to keep records for giving you grades anyway. Ultimately, the academic cell will want to see what is the basis behind giving anybody marks. Okay, so we will meet tomorrow then. Is it okay if nobody has any other questions?
Yeah. I had a
Yeah.
question about the singlet representation she showed, like as yeah, could you open it? Yeah, the
Which one?
3 rows one. I
Okay.
mean,
Okay.
the one in 3 cross 3 bar equals to 8 plus 1. Yeah,
Okay.
this one, the 0 0.
Yeah. What about it?
I mean, Could you explain why exactly it's represented that way?
Okay.
Yeah, because if you just you said no rows, no columns, right? It should be an empty
Yes,
thing.
sir.
Yeah.
Yeah, for singlet,
Yeah. So exactly. Yeah.
for
Go ahead.
singlet, you won't have any Young diagram because it's how do I say? I mean, here I've given an example of why it disappears. It's just that it's convenient for us to not have the
So basically, instead of having this three column thing, three. So if you had a three column, that's what she is trying to say, right?
yes, sir.
Say if you had a three, say column with three elements in SU3, it's the same thing as not having one. So that's the same thing as having a box whose conjugate will be the two boxes. And that's actually the conjugate of one box. So if you just follow the rule that 3 minus 3, so if you just follow the numbering pattern, we will find that that's how it works. The basic idea is, strictly speaking, 0, 0 should have no Young diagram. And in general, the rule that you have to follow for SUN is if you have a column with n elements in it, that's equivalent to having nothing at all. So that's basically how you make connection with the SN. Again, the theory is really that for SN, you're borrowing it for SUN, the price you have to pay is this. That if you have a column with n elements, that effectively is an empty column. So you essentially have
And
column lengths only up to 1, up to n minus 1.
it's irrespective of any other columns having like any
Yeah.
other allowed number of rows.
Yeah. So
Okay.
if you have a column with 3 elements in SU3, you drop it.
Okay.
Like even in the last example,
That's
when we take
Yeah, that's
when we
exactly where that becomes very useful when you're actually building up representations by by the direct product calculation, where you would end up with n columns and you would have drop it. Right? You can see that there's n bar cross n bar had n minus 1 boxes in a column, n had only one, and then where you would put the box.
yeah, so we'll take this one box. We can either add it to the first row or we'll add it
To the
to the
bottom.
nth row. Yeah.
Yeah, but if you add it to the bottom of
In
the first column, then what you will end up with is an n, something which is empty basically. So that's a singlet. Can of course also figure that out by the hook rule, right? That is dimension 1.
Yeah, yes, sir. It will be n factorial by n factorial.
Yeah. Well, the hook numbers will be 1, 2, 3, n going upwards, and the boxes will be labeled n, n minus 1 going downwards. The same n numbers in different orders.
It will be
Yeah, n at the top. The boxes will be labeled n at the top, then n minus 1, then n minus 2 down to 1.
yeah.
The hooks on the other end will be 1 at the bottom corner, 2 for the upper one, 3 for the upper one, and so on. Oh, in fact, it will be the same thing.
That's
Sorry.
the same thing.
It will be the same thing. The hooks and the labels will be exactly the same, not the different order. By the way, can you just say one thing? Suppose you had a same Young tableau representing an SN representation or an SUN representation. Which one will have larger size?
I mean, if
So it's
you
the same tableau,
yeah.
but representing an SN representation on the one hand or an SUN on the other.
We, I mean, we can't really say, but if the Young diagram has a lot of, I mean,
Well,
it's
actually,
not
you can, right? For SN, it's
SQL.
actually n factorial by the hook length, right?
Yeah, yeah,
And for SN, SUN, the calculation is slightly different. The numerator is different.
yeah. I mean, it's greater. Usually, it'll be greater or it'll be equal.
Yeah, it has to be greater than or equal because the numbers which you put in those boxes would be bigger in general.
Yes.
Right? In Sn, you could just imagine that you're putting 1, 2, 3 up to n and then multiplying them together. Right? Here
Yes.
you're not doing that. Here you're putting n on a corner, but you're actually increasing beyond that on one side.
Yes, sir. So it will be
Oh.
greater for SUN.
It will be greater than for SUN. The only case when it will be equal is that you have a single column.
Yes.
Okay, anybody else with a question? If not, let's call it a day today. Tomorrow at 4 o'clock, let's meet again. Okay, let's stop the recording and